Okay, so I think we can get started now. This event is being live streamed, as you, Michael, agreed to it. So our next speaker is Michael Betancourt. He's the principal research scientist with Symplectomorphic LLC, where he develops theoretical and methodological tools to support practical Bayesian inference. He's also a core developer of STAN, where he implements and tests these tools. And before moving into statistics, Michael earned a Bachelor of Science degree from Caltech and a PhD from the MIT, both in physics. So now we can go over to you, Michael. We will have 40 minutes of talk, followed by 50 minutes of questions, and then to the break.
Cheers, thank you so much. Thanks for the invite. Just two notes before getting started. I'm a little under the weather, so apologies for the voice. And second, due to the time constraint, I'm going to jump in, kind of have a very light intro, jump into some technical details, not too deep, but I'll be around for the rest of the week. So people have questions on any of the motivation, any of the technical details at the end. Don't hesitate to ask questions on the Slack, either today, this afternoon, or later on in the week. So today I want to talk about something a little bit different from what we saw this morning for me, this afternoon, I guess for some of you, where we'll use differential geometry not so much to work with quote unquote exotic spaces, but rather trying to develop methodologies and really understand methodologies to scale to very complex problems. This is work done in collaboration largely with Alessandro Barp, who's done most of the mathematical innovations here. But I'm going to kind of give a focus on kind of the practical side of things and why this might be useful for actual algorithm development. And so this is all about kind of taking an established algorithm, Hamiltonian Monte Carlo, and using its geometrical foundations to really understand what are the critical features, and then pivoting around those critical features, trying to understand how we might generalize, and what is the kind of full kind of plateau of possibilities while maintaining those ideal properties. So the first thing to talk about here is what is our goal? What is our target? And this is a circumstance where I have to admit I'm very much an applied statistician. So I'm not considering a machine learning perspective where we're going to try to learn from data. Rather, I'm going to presume that a practitioner, a collaborator has come to me with a model, a fully fleshed out, complicated, high-dimensional model encapsulating a tremendous amount of domain expertise. And that model has been conditioned on the data, resulting in a posterior distribution. And now our only goal is to extract information from that posterior distribution. So the posterior has been constructed, the model's been constructed, the data has been observed, all we're left with is the posterior. Now, the way we interact with that posterior is with expectation values. So if I want to ask a question about my system, if I want to construct an inference, I phrase that question in the form of a function, and the posterior returns to me an expectation value, right? This is the main kind of input-output of probability theory. So if I have a user-specified model, a user-specified posterior distribution, it's very unlikely that it's going to be mathematically convenient. I'm not going to be able to do these integrals analytically. And so I'm going to have to rely on numerical approximations to the expectation values. And this is where things are going to start to get tricky. One thing I really want to emphasize here is when we're working with complicated models and really tricky applications, uncertainty is really paramount. And uncertainty is quantified in these expectation values. And so while we can't return accurate approximations to these expectation values, we're not really getting a faithful picture of what the posterior is trying to say. If we are collaborators put a tremendous amount of work into building this model, we're really not going to do that model justice if we throw in some sloppy approximations. We really need to understand, have a model, a methodology for approximating these integrals that not only scales well, but has some kind of quantifiable error. That's the real kind of standard for doing statistical work. So numerical approximations of integrals, right? Kind of abstracted the problem away from kind of hit all the statistics and how that model was constructed. And now we're just kind of thinking about this high-dimensional integration problem. You might think naively, we'll go to something like a quadrature, right? This is kind of your standard low-dimensional estimator where you discretize your space into a bunch of points, and then you do essentially a Riemann sum, right? So you kind of take the plaquettes, if you will, between the points, compute the volume in that, and then use some kind of representative value whether it's at the center of that plaquette, on the corners, and then just add all of those up, to add those contributions up, right? And as the kind of density of the grid gets higher and higher, you get smaller and smaller distances between the points, that should converge to the true expectation value, or the true interval. And in some sense, that largely works, at least if you assume infinite computational power, but we don't have infinite computational power, right? What matters here is what can we do with a finite amount of resources available to us. And the challenge with something like quadrature is that scaling prevents us from doing anything all that useful. So if we kind of just do a standard back of the envelope calculation, the cost of the quadrature is going to be roughly the number of points. So I'm going to need an evaluation of my integrand at every one of these points. In 2 dimensions here, you can see that if I have n points in every direction, I'm going to need something around n squared, order n squared function evaluations, which doesn't seem that bad, but when you go to 3 dimensions, n cubed, 4 dimensions, n to the 4th, etc., it's a classic exponential scaling that we don't win against. The number I like to throw around, if you have a 100-dimensional model, which is not that high dimensional, and you want 10 grid points in every direction, which is a very crude grid, which is going to give you a terrible approximation, that requires 10 to the 100 points, right? That's about the number of particles in the universe. Back of the envelope calculation, as kind of fuzzy as particles can be. And so, this thing that might sound okay for 1 dimension, 2 dimension, to rationalizing it's going to be okay as you go to higher and higher dimensions, the cost turns on so fast, it's just not something that's going to scale. But maybe if you look at this picture enough, you might start trying to argue that there's that kind of scaling, that kind of exponential scaling is due to some kind of inherent inefficiency. And so if you kind of look at kind of squint a little bit and look at all this white space here, you might argue, well, can we avoid all of that counting? Can we avoid an exhaustive search of the space and just focus on computation on those regions of the parameter space that contribute to these integrals most strongly, right? And all these regions here that are white aren't really contributing to the integral. So is there a smarter way of doing a quadrature? And this is a potentially promising avenue, but we have to really narrow down what that means. What is a relevant region? Where do we want to focus our computation? Now, most arguments start focusing on the integrand. Certainly when the integrand is 0, we get no contribution to an integral. If the integrand is larger, we'd expect a larger contribution to the integral because integration is a linear phenomenon. So this seems like a promising place to start. In fact, we can go one step further and argue that the functions that we're typically looking at here, things like the identity squared, they're relatively uniform, at least compared to the kind of posterior densities we might be considering. We have kind of exponential tails. And so the kind of shape of the integrand is largely dominated by the shape of the posterior density function, or really whatever target density we happen to have. And so we can focus on our computational resources in the neighborhood where our posterior density is the largest. And so if we kind of think about this in a radial picture, we have kind of on the left here, the center, the mode of our density. We have the kind of radial distance. So think of this as a high dimensional picture, but just looking kind of radially as we move away. And we have this kind of exponential decay of our density. And that, just kind of this naive reasoning would suggest that we focus our computations in the neighborhood around this mode. It seems to align with a lot of arguments that everything should be an optimization. So we just run an optimizer, it gets the mode of the density, maybe put a little bit of fuzziness around that mode, done, right? Unfortunately, no. And the problem is we've forgotten something very, very important here. And that's that little DQ. That DQ is not just some notational shorthand in the integration, right? It's really informing what integration is. Integration is not just summing up points, it's averaging points over a volume. And that volume is really critical, especially in high dimensions. You can have a region where the integrand is quite large, but if that region has relatively small volume, then the overall contribution to the integral can be quite negligible. Whereas if you have a very large neighborhood that is a very small integrand, the kind of overall contribution can be much larger than you might have expected. And in fact, as we go to higher and higher dimensions, that contribution from the volume gets more and more important. And what we start getting is this kind of tension where there's kind of infinitely more volume towards infinity, or our volume's kind of concentrating around infinity. Our density is concentrating around some point, and there's kind of the pole is in the different directions, right? Now, what really matters for our integral is neither of these two contributions on their own. What matters is the product. It's the differential probability mass. And that product, right, is going to concentrate not at the mode, because not enough volume. It's not going to concentrate at infinity, because not enough density. It's going to end up concentrating somewhere in between. It's compromising between these two extremes. And so what's left is this concentration of our probability, not probability density, but our differential probability mass, concentrates in some neighborhood between the mode of our density and infinity. And remember, this is a radial picture here. So really what we have is a kind of fuzzy surface that's surrounding the mode. And so kind of borrowing from information theory, we can call this the typical set. This is the kind of a neighborhood that kind of best compresses our probability distribution. But really in this picture that we've been talking about, it's the region that best contributes or dominates the contributions to these integrals. And so if we kind of abstract it away a little bit, our target here is not thinking about this integration problem as an optimization. It's a fundamentally different operation. And so the right abstraction here is thinking about a fuzzy surface. And as you go past 4 or 5 dimensions, the surface gets so thin that it's basically just a surface, right? The fuzziness isn't that much of a factor. And so this helps explain the challenges of high dimensional integration, right? The thing that we're trying to quantify is this kind of fuzzy surface. It's bumping and moving and fluctuating in these weird ways we don't really understand, we can't really predict, and we have no idea where it is. And so if you try just throwing random darts around, you're not going to find this thing accidentally. It's just too small of a cross-section. If you put down a grid and the grid is too crude, the surface is going to snake right through those points all the same. It's only until you get a very dense grid that you're able to have some chance of really quantifying this. And of course, the dense grid requires that exponential scaling of cost. So this provides some sense of why the quadrature is so expensive, why any method is going to be expensive unless we can directly quantify this surface, this typical set. And so this is the challenge of scaling integration to high dimensions, which is fundamentally the same problem of scaling Bayesian computation to high dimensions. So to kind of build some motivation for how we can improve upon quadrature is we need to start thinking about methods that can take advantage of the structure of the surface itself. What we want is some kind of coherent motion, some kind of coherent exploration that knows when it's leaving the surface. So it can kind of surf through this region of high probability. If we move away from the region of high probability, we're able to kind of pull ourselves back, or we fall back in. And if we kind of move away on the other side, we come back in, right? But that kind of self-correction keeps us in this region of high probability, which allows us to move as fast as we can. And so this is just some kind of a rough, kind of intuitive motivation for what's going on. But if we want to turn this into some, an actual explicit algorithm or motivate an explicit algorithm, we need to start thinking about what this might mean mathematically. So what kind of properties describe or characterize this kind of coherent motion? So I'm going to argue there's 2 main properties that we're looking for here. The first is I want measure preserving transformations. So I want some kind of transformation that preserves my target distribution under a push forward. So push forwards are defined by the kind of push forward probability operation. And intuitively, all this means is that if I have a point in the typical set and I apply this transformation, I'm going to stay in the typical set. If I'm outside the typical set, I'll stay outside the typical set. But these kind of transformations ensure that once I'm in the typical set, I'll stay there and just move around, right? But that is not enough to guarantee coherency, because a diffusion is measure preserving, and diffusions don't have that coherency that we're looking for. They can double back on themselves. They have the kind of characteristic square root of n growth, and we're really looking for something that's more linear in its exploration. And that linearity, that coherency, comes from something called the flow. So a flow is a collection of transformations indexed by, in this case, a real parameter t. And the idea is that this family of transformations has a certain group structure to it. So if I take 2 of the transformations and I compose them together, I get a new transformation in this family whose index is given by the sum of the 2 component indices, right? So it's a one-dimensional Lie structure for those familiar with the term. And that seemingly simple structure implies a tremendous amount of consequences. The first is that the identity operator, or the identity map, is given by 0 index. And then the inverse of any map is just the minus of the index, right? So if I want to invert the action of some transformation I applied, I just find the transformation with a minus index, right? Because I just take t minus t, compose them together, I get t minus t, which is 0, which is the identity. And so what this implies is if I have, some element of this family, I can decompose it into a bunch of little additive contributions. And because all of those additive contributions have a positive index, none of them can be inverses of any other, right? So there's no doubling back anywhere along the path. It doesn't matter how I decompose the path. I can decompose the path into big chunks, little chunks, differential chunks. I never undo the action of any of the transformations that I previously applied. And so this pushes me forward as I take this time index from 0 to a positive value, or I can also do 0 to a negative value. The sign doesn't really matter so long as I'm consistent with it. That pushes me forward away from where I started. And so if I take these two ideas together, I take a measure-preserving transformation to stay in the typical set. I take a flow to make sure I have coherent exploration. And I have a measure, if every element of that flow is also measure-preserving, so I have a measure-preserving flow, that will ensure coherent exploration that stays in the typical set. And so this is what I argue is kind of the foundational challenge of computational statistics. How can we construct these measure-preserving flows for a given arbitrary distribution, right? This ends up being a very hard challenge. You can come up with measure-preserving flows of very nice systems, very symmetric systems. If I give you some very complicated distribution, motivated by an application and not any kind of mathematical nicety, you're not going to be able to come up with just engineer a flow on that space directly. But this is where our miracles start to come in. And so our first miracle, our first kind of geometric miracle in our conspiracy here, is that there is a special kind of space where there's a very natural measure-preserving flow. There's a very kind of natural flow structure to it. There's natural measure structure to it, and they integrate together in a very nice way. And so here I'm going to get a little bit technical. And again, if there's any questions about this, I'm happy to kind of talk about the geometry in the Slack. So let's assume that our target space here is a manifold. So that a nice, smooth, clean space, just like the real numbers, just a little more general. And we're going to impose certain kind of structure to this space. Give it what's called a symplectic structure. So this kind of exotic, if you will, structure immediately implies a lot of nice things. So one is it allows us to automatically map functions into vector fields. And vector fields, just little arrows in space, give us trajectories, which turn into a flow. So if I have an arbitrary function h, I can take the derivative of that function, and then that derivative combines with the symplectic form to give me a vector field, right? So you give me any function you want, I turn it into a vector field, I can then integrate that vector field, and that generates a flow. So basically, for free, I can always construct flows, which is a pretty nice operation to have. But that's not it, right? The other nice thing that the symplectic structure allows me to have is the natural probabilistic structure. So there's a canonical uniform measure, kind of a nice uniform measure, reference measure that's defined for any one of these spaces. And it's unique. It's a special kind of measure. And I can take a function and I can weight that measure by that function and generate more complicated distributions. So I take my reference measure, I hit it with the exponential of a function, using the exponential here just to make sure things are positive. And that gives me a whole class of probability distributions, provided I can normalize this. And so we had this kind of nice map from functions to vector fields and then flows. And now there's this nice map from functions to measures. And what's really exciting is these are two compatible transformations or two compatible structures. The flow that I get from a function and the distribution that I get from a function are compatible in the sense that the flow preserves that distribution. And so if I can somehow manipulate my problem to have this structure, and I can somehow manipulate this function so that the probability distribution happens to be my posterior, happens to be my target distribution, then I already have the thing that will solve my problem. Now, having some kind of exotic geometry that solves the problem isn't necessarily going to be useful if I don't have that structure inherently to my problem. And this is where the next kind of magical miracle comes in. Because even if my space doesn't have a symplectic structure, there's a way to engineer it, to lift it into a higher dimensional system that will always have this structure. This is called the cotangent bundle construction. So what I'm going to do is I'm going to take my space here, represented by a line, and I'm going to attach at every point a copy of the real numbers. So if I have an n-dimensional space, I'm going to throw in a copy of r to the n. And I'm going to do that at every point in a kind of a nice, smooth way. So these are called fibers, right? And kind of weave the fibers together, you get a higher dimensional space called the cotangent bundle with a nice kind of projective structure. And it turns out that this cotangent bundle of any nice space has a canonical symplectic structure to it. And so if I can somehow take my system and I can lift it up to this cotangent bundle, then I have the symplectic structure, I have a measure preserving flow. I have everything I need to get this kind of coherent exploration, which is pretty miraculous given how rare these kinds of flows are. So to do that lifting, I need to take my probability distribution on the original space. I need to somehow define some probability distribution on this larger space. And so in terms of kind of probabilistic operations, I need a conditional, right? I have a marginal on my original space. I need a conditional on these fibers. And so that's just a probability distribution defined for every one of these new spaces. So I can have some variation in the distribution for every one of the fibers. That defines, this is kind of mixing some geometric and probabilistic notation here, a conditional distribution for these fibers given where they're attached. I can write this as another function times a little kind of uniform measure over the fibers. And then the kind of geometric correlation to this is I have my original distribution, I pull it back against the cotangent projection, I wedge it against this conditional, and I get a joint distribution over this over the cotangent space. And so because of this kind of just coincidence that every space can be lifted to a cotangent bundle, and the cotangent bundle has exactly the structure we need for this coherent exploration, then I'm all set to take advantage, to build an algorithm. So what I'm going to show you here is kind of the basic construction of Hamiltonian Monte Carlo, where on the left we'll have our original space Q and our target distribution pi. On the right we'll have the cotangent bundle. And so the first thing I do is I lift up my target distribution to the cotangent bundle. And so again, this is just choosing a conditional distribution. You might have heard about this as kinetic energy, it's sort of an equivalent object. Once I have this joint distribution, I can compare it to the reference distribution, and that ends up giving me a function. So more formally, it's the minus log of the Radon-Niken derivative of the joint distribution relative to that reference measure. And then once I have a function, I have a flow, right? So basically what I'm doing here is I'm choosing this function so that e to the minus h times the reference measure is this lifted distribution. So the distribution tells me a function, that function then tells me a flow, and by construction, these are compatible with each other. So that flow preserves the joint distribution, and in fact, the projection of that flow preserves the original target distribution. So we're going to lift up and go around and then come back, and that's going to give me the exploration that I wanted on the original space. Or to kind of show a little cartoon, here's our higher dimensional cotangent space. We have our original direction Q, original space Q horizontally. We have these additional dimensions P vertically. The red here is kind of cartoon of the typical set of the joint distribution. And Hamiltonian Monte Carlo then proceeds in a series of lifts, flows, and projections. So we start off with we start off in the original space. We sample from the conditional distribution that lifts us up randomly to this higher dimensional space. Once we're on the higher dimensional space, we can flow. And then when we decide that we've gone far enough, we can stop, project back down, and this gives us a new point that's far away from the initial point, but stays in the original typical set. And then we just repeat this over and over again. We lift, flow, project, lift, flow, project, lift, flow, project. And so these are the basic kind of iterative elements of what will become the Hamiltonian Monte Carlo algorithm. But one thing I want to point out here is that there's a kind of a natural geometric structure here. It turns out the flow is energy preserving or Hamiltonian preserving. This function that we constructed doesn't change along the flow. And that means we can decompose this whole thing into motion along these level sets and then motion between the level sets. So really what we're doing is we're exchanging these motions that jump between the level sets that explore the energies, these Hamiltonian values, and then moves that explore the level sets themselves. And this gives us a really nice kind of theoretical way of understanding how the algorithm works. We can kind of break this complicated transition into multiple steps, analyze those steps separately, and then bring those analyses together. And this gives us a lot of kind of theoretical tools to work with and understanding not just how the algorithm works, how it doesn't work, and then how to optimize it when it does work. So this would be Hamiltonian Monte Carlo if we lived in a perfect world, right? Now, the challenge with Hamiltonian Monte Carlo in practice is that integrating a vector field to generate a flow is basically solving a system of ordinary differential equations. That is not something we can do analytically, at least in all but the simplest cases. So just like integration is hard, integrating a vector field is also hard. But our next miracle shows up because these aren't just regular ordinary differential equations. These are very special ordinary differential equations. And it turns out they emit very, very special numerical solvers. These things are called symplectic integrators, and they take advantage of the linearity of these vector fields. And so what we're looking for here is a way to approximate the exact vector, the exact Hamiltonian flow. And we're going to do that by splitting up our Hamiltonian into a sum of terms. And the idea is that the Hamiltonian breaks into a sum of terms because our vector field is linear. The Hamiltonian vector field generated by that Hamiltonian turns into a sum of vector fields. And once I have a sum of vector fields, I can now apply the Baker-Campbell-Hausdorff theorem to turn that into a matrix, or kind of a matrix exponential-like operation to kind of show what happens when I approximate the summed flow with a bunch of component flows, right? It gives us a nice kind of error control mechanism here. And it turns out with kind of working through this procedure, we also get some very nice conservation properties here. This leads to something called a structure preserving integrator. It doesn't exactly solve our problem, but it maintains most of the symmetries and conserved quantities, which kind of really constrains what kind of errors can arise. In particular, here I'm just showing you the local error, but the global error has a very similar scaling to it, even though you might expect the global error to aggregate, and indeed it does in many other numerical integrators, right? Kind of a classic Runge-Kutta, the error tends to grow with integration time. Symplectic integrators, it does not. And that, excuse me, has to do with the conserved quantities. So that structure preservation gives us something that looks like this. So this is our exact level set. And if we had an exact integrator, it would be constrained to this level set because that Hamiltonian function is exactly preserved. Our symplectic integrator isn't perfect, but it's pretty good. And the error tends to oscillate as it moves around. It starts off at zero error in terms of this Hamiltonian function, and then it gets larger, and then it gets smaller, and then it gets larger, and then it gets smaller. But there's kind of this kind of global constraint to it. It doesn't drift, it doesn't grow in most cases. And so this gives us a very kind of powerful way, a scalable way of integrating these Hamiltonian vector fields into an explicit algorithm so we can actually implement on a computer. And on top of that, because these symplectic integrators conserve so much structure, or they preserve so much structure, they actually allow us to exactly compensate for the numerical error with some probabilistic operations. And so I don't want to go into too much detail here because we don't have the time. But one way to do this, kind of one of the more general ways of doing this, is to think about sampling entire trajectories. So if you can think about a numerical trajectory as just a collection of points, kind of stemming out from your initial point, there's lots of trajectories that you could build around a given point. So in this case, if I'm going to integrate for 4 steps. So I have 1 point, 1, 2, 3, 4. I get 5 total points. There are 5 trajectories that could contain the initial point. I could integrate forwards 4 steps. I could integrate backwards 4 steps. Forwards 3 steps, backwards 1 step. Forward 2 steps, backwards 2 steps. Forward 1 step, backwards 3 steps. Right. all of those are valid trajectories that I could have generated from that initial point, right? Or in other words, trajectories that contain that initial point. And so what I'm going to do here is I'm going to sample from those uniformly. I'm not always going to integrate forwards in time. I'm going to kind of balance integrating forwards and backwards in time by randomly choosing one of these trajectories. So I'll sample one of those uniformly. And then I'm going to pick one of those points based on their Hamiltonian values. So essentially, if the Hamiltonian gets very large relative to where it started, then the weight of choosing that point gets very small. And it turns out, with that two-step procedure, we exactly can't compensate for any numerical error introduced by the symplectic integrator. Amazing coincidence that this all works out so cleanly. And it gives us something that you can implement in, if you want to be fancy and, really have, care about your vertical space, 10 lines of Python code, R code, C++ code, whatever your favorite language is. The kind of basic Hamiltonian Monte Carlo construction, not that complicated to put together, but the math behind it is incredibly intricate. One of my most favorite properties of all of this has to do with how Hamiltonian Monte Carlo fails. So I mentioned that when we have our symplectic integrators, there's a structure preservation to it, right? And in most cases, the energy is bounded because of the structure preservation. And so as we continue to integrate for longer and longer times, the error just tends to oscillate around the true value. And we don't get a kind of growing or a drifting error, right? We don't get a spiral outwards. We're kind of confined to this finite volume. And that's true most of the time, but not always. So whether it stays at a finite error or not, excuse me, is related to the stability of the integrator. So this is a stable symplectic integrator. And what we can show is that if we get rid of the arrows and just focus on the points, that those points happen to lie on their own level set. The symplectic integrator has its own geometry that it exactly solves for. And we can compare that geometry to the geometry of the problem that we're trying to solve for. So instead of trying to compare the numerical solution to the true solution, we can just compare the shadow Hamiltonian geometry that's exactly solved by the symplectic integrator to the exact Hamiltonian geometry that we're trying to recover, and use that to characterize how the error in the integrator, how the error propagates and has consequences to our algorithm. So incredibly powerful theoretical tool. Leads to, for example, things that we choose the optimal step size in the algorithm. But it also tells us something about that stability, right? Because that stability is really a question of the topology of the shadow geometry, of these shadows level sets. So if we have a stable symplectic integrator, then the topology of the level sets are preserved. So if I have a compact level set initially, then I have to have a compact level set. My symplectic integrator geometry also has to have a compact level set. And I have two compact surfaces, they can only be a finite distance apart, right? And that's where we're getting this global energy conservation, or global error, error bound. It doesn't matter how long we integrate, we're always going to be confined within those two surfaces. But sometimes we get an unstable integrator. We have an unstable integrator, the topology shifts. And so if I start off with a compact level set, then I can't maintain a compact level set. I get something like this. And so in this case, the symplectic integrator jumps off to infinity really, really fast. And so we get this really nice geometric picture of why the symplectic integrator is either stable or not stable. And this really kind of powerful intuition that either Hamiltonian Monte Carlo or your symplectic integrator is going to be very stable very quickly, or it's going to be very unstable very quickly. These are two very, very different behaviors. And that's incredibly powerful because it turns out when you start applying this to probabilistic problems, the kind of pathologies that tend to obstruct accurate integral computation due to the kind of classical kind of degeneracies in your posterior distribution are exactly the kind of features that will cause these unstable symplectic integrator trajectories. And so we look for these particular behaviors. We look for our numerical trajectories running off to infinity that tells us something about the problem that we're trying to solve, which we can then use to investigate, understand something about our target distribution, our posterior. And this is an incredibly powerful tool. There's a lot of understanding about methods that have been in use for decades, but it's only with this kind of very clear picture and ability to identify these pathologies, the source of these pathologies, and really understand what's going on, and really identify problems that people have thought we've been solving fine for a long time, but actually have not. And so this is kind of a lot of where my work goes these days, is trying to use Hamiltonian Monte Carlo to understand problems and really thoroughly investigate them and find all of these problems that people have taken for granted. So that is kind of a very, very quick introduction to Hamiltonian Monte Carlo. It is a kind of magical construction. It relies on this very coincident set of miracles, that having this symplectic geometry that intertwines probability and geometry and flows. Having the cotangent bundle always have that structure. So we can always take if our problem is to find out a manifold, we can always lift it up and take advantage of that structure. But none of that would be worthwhile if we couldn't numerically integrate those trajectories in a way that preserved a lot of that structure. And the symplectic integrators, the next miracle that falls on top of that. The Hamiltonian vector fields themselves are pretty miraculous. They only depend on the gradients of your Hamiltonian function, which then rely on the gradients of your posterior density function, things that are pretty straightforward to take advantage of. They don't require any kind of complicated mathematical operations that require further approximation. Everything just falls together in this miraculous way. And the more you study Hamiltonian Monte Carlo, the kind of stranger it seems that it all fits together. That in the early 80s, a bunch of people working on lattice QCE just kind of put some things together, and it happened to work. And it worked so perfectly that to this day, that basic structure is still in line. So we might then ask, just how much of a coincidence is it? Is this the only way to get this kind of behavior, or are there other ways of satisfying all of these properties, satisfying all of these miracles? What is the most general miracle that we could put together? And so this is what really led to this more recent work, which was trying to kind of take the important features of Hamiltonian Monte Carlo, reduce them down to kind of as simple mathematical criteria as possible, and then build up mathematical theories for those individual behaviors. So I'm going to list here 5. These are still very much in draft, so don't take them. They might change in the future. But kind of one perspective on this is, here are the 5 properties that are really why Hamiltonian Monte Carlo worked as well as it did. 1, we have an explicit map from a target distribution or a target measure to a measure preserving vector field. Right? So I can take a distribution and I can immediately find a way of generating motion, generating exploration that preserves that distribution. 2, a linear map from functions to derivatives to vector fields. Now, this one I didn't emphasize probably as much as I should have earlier on. If you give me a flow, I know no guarantee I'm going to be able to implement that flow. 1, I may not be able to integrate the vector fields, but 2, I may not be able to implement the vector fields themselves. Vector fields that only depend on derivatives are particularly nice and very particularly amenable to implementations. So having something that just takes functions like posterior density functions, turns them into derivatives, and then turns those derivatives into vector fields, those are the kind of things that are basically limited to do in terms of practical implementations. And then if we want to be able to have both of these, if I want something that preserves the target distribution but is also implementable in practice, I want something, a vector field that's measure preserving and derivative driven. And then to ensure that I can actually implement those vector fields, I want structure preserving numerical integrators like the symplectic integrators. And then I want some kind of general error compensation mechanism. And I outlined very, very briefly kind of a general way of thinking about how it's done in HMC. But any kind of way of correcting for error exactly to ensure that we can stay, if we kind of drift away from the typical set, we're able to ensure that we reject that and go back to the region of high probability. And so, as I mentioned before, I'm going to very, very, very briefly run through these just due to time. There's some incredibly beautiful geometry here. I'm happy to talk about any of this in the Slack as well. So for those who are interested, I'll see you there. Okay, so just in step, our 5 criteria, here's how we construct those. So in order to construct a general measure-preserving vector field, Alessandro came to this idea of bringing in this old operator called the rotational. And the rotational is basically a measure-weighted derivative. You take the exterior derivative and you compose it with some kind of transformations that depend on the measure. And so it's kind of, you can think about integration as kind of summing things up, but locally weighted by a distribution. This derivative operator is basically doing the same thing, except it's locally weighting the local change of a function by this measure. So if the measure is or in a neighborhood of low probability, the derivative is going to be small, even if the function is changing. Neighborhood of higher probability, derivative will be amplified. Now, what's interesting about this operator is that it preserves a lot of the structure of the exterior derivative. So in particular, it's nilpotent. So if you take the operator, compose it with itself, you get 0. And once you have this, now you start talking about having potentials. So if I take some 2 vector and I hit it with this curl or with this U rotational, we'll get a vector field, right? Now, if I take, the 2 vector here is called a potential because it parameterizes all the vector fields I could generate in this way. And then all of these vector fields have a very special property. So the rotational applied to this operator is just the rotational twice, which is 0. So any vector field of this form is measure preserving by construction. Now, the only thing we have to add to this to make sure it's a general theory is a topological term. And so you add there's a whole homology here that you can construct from this operator. You get a kind of measure-induced topological structure. You add those corrections and you get your general form. So anybody who's done kind of more theoretical physics and has kind of dealt with vector potentials, this is the same kind of construction. So you get your vector potential, and then you have topological correction for the topology of your space. So that provides, again, not giving this justice, the kind of richness that's available here. The second step, linear maps from functions, derivatives to vector fields. This one is surprisingly kind of simple, but then is incredibly rich in the consequences that you can derive from it. The exterior derivative maps functions to derivatives, but I want to then take that exterior derivative and map it to a vector field. So really all I need there is a 2 vector field. And so that 2 vector field composed with the exterior derivative provides a map from functions into vector fields. And we call that the mechanics of B, and B would call a bracket. And so this bracket generalizes things like metrics, it generalizes symplectic forms, and a whole bunch of other kind of dynamical constructs that you might have seen, especially in the physics literature. And so you can take a lot of those ideas, things like Casimirs, invariants, invariant measures, a lot of things that kind of just come naturally from dynamical systems, you can start breaking down as separate properties of these brackets. Some brackets have those properties, some don't, but it gives you kind of a handle on what structures are generic, what structures are special. And then these 2 things are just kind of magically compatible with each other. So in particular, if I take 2 different measures, so I have mu and nu, and I take the same vector potential, so this is the 2 vector that we talked about before, I can construct 2 different vector fields, right? So I have this one potential, I have 2 different measures, I have 2 different rotationals, and so there are 2 different vector fields that I can construct from those 2 different operators. Turns out the difference of those 2 vector fields is a bracket vector field, and the bracket is generated, the bracket itself is that same 2 vector potential, and the function that generates this is where things get really cool, is the log random Nichian derivative between those 2 measures. And so you remember in HMC, we had a log derivative showing up, and that's how we got the Hamiltonian function, but it was kind of an ad hoc choice. Here, we're starting seeing it showing up very generically. There's a reason why it's e to the minus h and not just some other function of h. Excuse me. And so now what I'm going to do, if I want to really kind of understand the intersection of these two nice objects, measure preserved vector fields and these bracket vector fields that are easier to implement, what I can do is I can take a 3-vector field, hit it with this measure-induced derivative operator, this mu rotational, or in this case, a nu rotational. And that gives me a 2-vector, which I'm going to then use as my 2-vector potential. And so if I take that A and I plug it in, that guarantees that the nu term vanishes, because again, curl nu times curl nu is 0. And what I get is this whole thing. So once that term vanishes, the measure preserved vector field just reduces to that bracket vector field. And so it turns out this characterizes the intersection completely. By any kind of vector field of this form, where I choose a reference measure and I choose a 3-vector potential, that completely parameterizes all the dynamics that are measure preserving, or sorry, that preserve mu, that preserve the reference measure nu, and have this bracket structure allows me to implement them in an efficient manner. Completely lays out the space. Again, it's kind of a magical construction, but that's all we're looking for. And so when you put all stuff that together, we basically generalize all of the wonderful structural properties of Hamiltonian Monte Carlo. We get the same kind of level set behaviors. A lot of theoretical analyses can carry over in a very straightforward way. We're just replacing the Hamiltonian with this more kind of generic log derivative. And then magically, we can take the symplectic integrator construction, and that happens to also carry over immediately because we kind of designed it that way. And so you can construct these compositional integrators, you get backwards error analysis, you get these topological stability considerations. It's just wonderful. And then because you have that structure preserving integrator, the same kind of correction mechanisms that we introduced for Hamiltonian Monte Carlo just trivially carry over. The proofs are a little more complicated, but you know the basic idea is the same. And so it's kind of this magical, I don't want to say it. I think when you really start appreciating Hamiltonian Monte Carlo, it is a miracle that it works at all. So many things have to come together to make that happen. And once you appreciate what had to come together, you can start asking, how can we generalize? And there is this beautiful geometry that tells us how to do that. Now, what's interesting is it doesn't actually tell us whether or not the kind of generalization is actually much larger than HMC. And this is it's a somewhat open question. It doesn't look like it's that much larger. There's some special cases where you might get some useful generalization. But in a lot of cases, HMC is kind of the best, which is even more miraculous than where we started. So a lot of this work has yet to be published, but a lot of the kind of basics of it are in this archive paper if you want to check it out. Again, I'm happy to chat about any of it in the Slack. And I'll just end very quickly with one thing I want to emphasize here, in contrast to I think what you'll see in a lot of the other talks here, is most of the use of HMC is not on manifolds. Yes, you can use HMC on tori and spheres and configurations of molecules and all and stuff like that. But a lot of the use of HMC, especially with tools like STAN, is just on the real numbers, just on Euclidean spaces. The use of differential geometry is not so much to generalize the space we work on, but to separate out what is derivative and what is extraneous structure. What is actually differential information versus what's metric structure, distance structure, and things like that. When you work with classic calculus, those two things are really bound together. And so by framing everything in terms of differential geometry, we can separate out those structures and just understand what a derivative means. And that lets us do this kind of theoretical analysis without being burdened by this irrelevant structure. And so this similar kind of insights can happen from not only in probabilistic computation, but in optimization. Again, I'm happy to chat about that in the Slack, where we can kind of understand how things like Nesterov work from a very geometric perspective. And even things like automatic differentiation is a very geometric idea when you kind of step back and recognize what you're actually propagating back and forth. And so even if you're not thinking about playing with wacky spaces, taking this kind of differential geometric perspective is really powerful if you just want to understand what a derivative is doing. So yeah, so with that, thanks for listening. Apologies, it got a little wacky there. Fever's still a little high. But yeah, happy to chat for the next few minutes.
Thank you so much for that great talk. We have a few questions that we can go through. So the first one, Momchil asks, could you give an example of a typical set for a given target distribution? For example, what is the typical set of an n-dimensional standard normal distribution?
Yeah, so that's about the only example we can give because in anything else, it's not really analytically constructible. A lot of probability theory tries to get bounds on kind of how things move away and how the typical set behaves, but doesn't actually give an explicit construction. In the multivariate normal case, the IID multivariate normal case, it's essentially, if you look at the radial direction, so it's symmetric in the angular directions, and then in the radial direction, it's a chi density. And so you can, it's a chi with d degrees of freedom. And so as d is the dimension, so as d gets larger, then it moves away from 0, and then it also kind of shrinks relative to the distance from 0. I can provide a link that goes into more detail and has the actual integration showing that along with they're in R. I hope I don't offend too many people used to Python, but there's R examples that also complement the analytic calculation with some simulation code that also show that concentration behavior.
Okay, thanks. Yes, that'll be.
So yeah, I wanted this typical set idea is just a way to help us understand what not to expect in high dimensional spaces. That really just emphasizes that the mode is not that helpful when trying to characterize a distribution. And so we're never actually going to construct it in practice, right? The way we construct it is by generating samples or running a Markov chain or something like that. So the normal is like the one case we can build things up and use that as a bridge, but in most cases, it's just in a cartoon to help us understand what the sampler is trying to do.
Okay, thanks for your answer. Yes, it'd be great if you could provide that link probably in the Slack chat. That'd be great. Mm-hmm. Then Tim asks, measure preserving flows are rare. Are there any other classes aside from Hamiltonian flow? For example, Ricci/mean curvature flow or one of the other flows that come up in geometry? If so, are they useful?
Let me say, I asked that before you answered it in the second half of the talk, so sorry about that.
Oh, well, no, I mean, it's an important question, right? Because it like one thing I didn't really talk about is where does Riemannian geometry fit in there? So you can construct a bracket. That bracket geometry can be Riemannian, but you can't get measure preservation that way. So it doesn't fit at that intersection in a particularly nice way. So any Riemannian-driven flow is it's too gradient-driven, and so you're not going to get the measure preservation, right? The incompressibility that you need. So the other place they really show up is in group actions. So if you think about like the multivariate normal, the one way of constructing a measure preserving flow for the multivariate normal is just thinking about this symmetric spherical typical set, and then you just rotate it. So the rotation actions on preserve the typical set structure. So arguably the best generalization of measure preserving flow is having some kind of group action that is preserves your target distribution, and that goes beyond manifolds. You can think about that in more general discrete and non-smooth cases as well. So for particular examples, those would be the ones that are probably more familiar, is anything with a very symmetric structure to it.
Great, thanks.
Okay, and then let's go to our third question. Sharvari asks, could you explain the causes for the instability of this method? Is it because we're not in a typical set to begin with? And she's talking about the symplectic integrator for HMC with bounded E.
Sorry, actually, I'll just, I didn't get the full question. Oh, okay, yes. No, so the symplectic integrators, they rely on a discretization of the space, right? It's like any numerical integrator. You can't just make infinitesimal jumps. You have to make some finite jump. And if your truth system changes too much within that finite jump, then you basically lose track of where you're going. And so in something like a classic ODE integrator, there's a lot of kind of inertia to it. So you keep going forwards and you kind of lose track to where you kind of have gone off the path a little bit, but you keep going. And that leads to this kind of drift. So you get a kind of the slow aggregation of error that gets worse and worse with increasing integration time. With symplectic integrators, it's like you're driving a sports car, right? Where like you hit a little divot in the road and you start just like turning off a little bit, but instead of just kind of slowly drifting away, you just rocket off, get off the track and start, driving orthogonal to your track entirely. So the stability has to do with kind of how much your underlying geometry changes within that little step size that you've chosen. And if things are changing too quickly, then your symplectic integrator just shoots off and becomes problematic. And then because of all of this kind of global structure imposed by the structure preservation, those little the changes that are happening on those small timescales turn into this global topology in a very interesting way. And that's why we have all these wonderful properties that we can rely on. There's kind of this local global correspondence that happens. I don't know if that answered it. Again, I can try to answer more carefully if you can follow up on the Slack.
Okay, thanks so much for your answer, and thanks again for your talk. I think we can end it here. So if everyone wants to just say thanks to the speaker.